Okay, starting from this lecture, we move on to the next topic, which is ordinary differential equations. So in this lecture, we will discuss the nomenclature ordinary. What is ordinary about ordinary differential equations. We'll also look at some basic classification of differential equations, and then we'll set up the scene for our study of differential equations. Okay, so a differential equation contains in general many derivatives, and they're tied together in some some linear combination of these derivatives of some unknown function, and then they add up to some other function, or it can add up to 0, right? And our job is to find a function which satisfies such a linear combination of various derivatives. And it's an ordinary differential equation if all the derivatives involved are ordinary, meaning there are no partial derivatives, right? So if there is if functions depend on more than one variable, right, and their derivatives with respect to different independent variables are also contained in your differential equation, that's the more complicated kind, and that's a partial differential equation. So in general in physics we have lots of real world phenomena which actually give us partial differential equations, and then it's possible, right, in using certain techniques for certain class of partial differential equations to be able to recast these partial differential equations into ordinary differential equations, or a smaller set of partial differential equations can be recast as a larger set of ordinary differential equations. In any case, the study of ordinary differential equation and a solid theoretical understanding of ODEs is absolutely essential if you want to tackle the more gory problems which come up within the field of partial differential equations. And the theory of ODEs is extremely well developed, very beautiful theory, and so our job in the next several lectures is to make a thorough study of ODEs, right, from the point of view of a physicist, but we'll also go into the theoretical details, right? So okay, so let's start with classification of ODEs, right? So one immediate and very important class of ODEs that we will concern ourselves with is the class of linear ODEs, right? So linear ordinary differential equations are those in which the unknown function appears only in a linear fashion, right? The unknown function and its derivatives, all of them have to be linear. Such differential equations are called linear differential equations. So let's look at a whole bunch of examples. So I have all of these equations which I'm claiming are linear equations, right? So you have d squared y, you have the second order derivative of y appears here, but there is no square of this quantity, so it's linear in the second order derivative, first order derivative first, and the function itself all are linear. Therefore this is a linear differential equation. Now you can have x here, you can have the independent variable can be very crazy, nonlinear is allowed. So an example of nonlinearity is here, a very simple nonlinearity. You have x nonlinearity in the independent variable, so and that's allowed, and that's not really, so you wouldn't say that this differential equation is nonlinear, it's a linear differential equation, right? So when you're starting out, this is a point of confusion for a lot of students is they confuse between the x's and y's, the dependent variable and the independent variable. You should look at it carefully, and indeed this differential equation is also linear, because although you have x squared and in fact you have much more violent something like sine of x appears, it doesn't matter because y and dy by dx, both of these are linear. So likewise this also is a so x squared can appear here, x can appear here, sine of x can appear here, cos x can appear here, all kinds of possibilities as long as it's only to do with x. So all of these are linear differential equations. So let's look at a few examples of nonlinear differential equations to contrast against the first set. So now you see that if you have a sign of y, then that's trouble. So that's a nonlinear differential equation. So if you have y squared, that's also a problem. And dy by dx the whole squared plus xy is equal to 1 is also a nonlinear differential equation. So in general, nonlinear differential equations are very hard problems, and there are very small, very special subclasses of problems only are amenable to exact solution. And even when there are solutions, there's so much complexity. So in fact, the field of nonlinear differential equations is a whole subject by itself, right? It would be, there is so much rich phenomena associated with nonlinear differential equations. This whole topic in itself, it gives you lots of exciting phenomena come out of this, right? So we don't, it's not the focus here for us to go into all of those properties, but our goal here will be to make a generic study of differential equations, right? So this is one classification at this point. So another, so linear ODEs have this very special form. There's a linear operator. It acts upon the function, the unknown function y of x, and it can give you some other function of x. So that is allowed, right? So this operator is linear, and so a key property of linear differential equations is the so-called superposition principle. So, but okay, before we come to that, let's also quickly point out, another, I guess, a definition or further classification of linear ODEs is, those linear ODEs in which this right-hand side f of x is equal to 0, they are called homogeneous if there is no driving term, right? So in homogeneous differential equations are also going to be studied in our theory, and oftentimes there is a close connection between the solution of the corresponding homogeneous differential equation and the full-blown homogeneous differential equation, right? So in that context, it's useful to be able to first study, the simpler problem where you put f of x to be 0 and then you bring in f of x and then you work out the more general differential equation, the solution to the more general differential equation, right? So in general, an explicit form for a general linear ODE, right? You can write it like this: a naught y plus a1 y prime plus a2 y double prime, so on, all the way. It can go to whatever order equal to b, provided the a's and b's are either constants or functions of x alone, right? So that's important, right? You can have functions of x, and that's not a problem. It still will be called a linear differential equation. So when you have a linear ODE, the superposition principle holds, which means that if you can find two different solutions, then an arbitrary linear combination of these two solutions is also a solution of the ordinary differential equation, right? So this will break down if there is any nonlinearity in y, right? As you can take up some simple example and check it for yourself. So the thing about linear differential equations is that superpositions of solutions are also solutions, right? So it's a key aspect of linear ODEs. Now there is another notion which we have sort of already mentioned, but let's make that explicit, and that's the order of a ODE, right? So sometimes, particularly early on in the study of differential equations, students get confused between order and linearity or nonlinearity, right? So let's look at a few examples. So the order of a differential equation is the order of the highest derivative of the unknown function, right? So if we'll collect a bunch of examples from the examples that we have already looked at, right? So we took all these examples and broke them into two bins, one of which contained linear equations and the other bin contained nonlinear differential equations. But we could have also broken this down into order 1, order 2, and so on. So the examples of differential equations with order 1, right, from our collection of differential equations are all of these. So if I have x squared dy by dx plus x squared y equal to sine x, there's no problem if you have sine of y, it's all good, as long as you just look for the highest derivative, So as far as this classification is concerned, you only look at the highest derivative and you see dy by dx the whole squared appears, it's not a problem, right? So there is no second order, it's the first order differential equation. It's a nonlinear differential equation, but it's a first order differential equation. And so likewise you have dy by dx and you have y squared, right? So it's a nonlinear differential equation, but it's first order and order 2, right? So this is order 2 and linear, and this is also order 2 and linear, order 2 and once again it's linear, right? So you can cook up examples where you can put in a sine of y or sine squared of y cube, I don't know. So you can come up with all kinds of very complicated terms. I mean, you may not be able to solve them, right? At this point, it's only an exercise in classifying differential equations. So you can construct, as complicated a differential equation as you want and identify their order. Okay. Now, order phi, I have just made up one other example. So I can think of something like x to the phi, d to the phi, y by dx to the phi, plus x to the 4 and so on, all the way up to y is equal to cos of x, right? So I could put whatever function of x on the right hand side, it's still an order phi. So as long as there is this d to the phi by dx phi, even if all of these other terms are absent, it's still a fifth order. And so in general, so you can say that a linear differential equation of order n has the following general form. So now I'm saying I'm putting a linear differential equation. So I have an of x dn to y by dxn plus an minus 1 of x dn to n minus 1 y divided by dx to the n minus 1, so on, all the way up to a naught of x y is equal to b of x. So the essential requirement for this to be order n is that an of x should not be identically 0. If it were, then it would be a differential equation of a lower order, right? So an of x is definitely not 0, right? It could be a constant, it could be some other non-trivial function of x, doesn't matter, right? And all of these other coefficients are also, you're free to choose them to be functions of x, no matter how complicated, no matter how nonlinear in x. It's not a problem, but it's still, this overall differential equation would be linear and it is order n if an of x is non-zero. Okay, so that's an introduction to ODEs and why we call them ODEs and some basic concepts pertaining to order and so. So that's all for this lecture. Thank you.